you ordinarily see, the best way to describe what the phenomenon, colors of things, the softness of materials, the weight of things, the way their temperature, when you change the temperature, how much heat it takes, sounds, and a whole each phenomena. The only best way to describe it is to describe the phenomena that are not included in this theory. And one of them is the accelerations produced by gravity. The force of gravity is in another theory, gravitational theory, or general relativity. Another range of phenomena have to do with exciting the interior of nuclei, nuclear physics, protons and neutrons, radioactivity, and nuclear phenomena. That excluded, all the rest of the phenomena of nature are contained in this one theory. Now you can see why it is that I feel a bit uncomfortable when someone asks to give a talk, please tell us the latest things, because then I'm talking about our problems that we have in trying to understand the insides of a proton. For example, for a proton, to tell you a contrast, our understanding of the outside of the atoms, the electrons and light that I'm going to talk about, the theory about Joule and rate of heat.
So he really felt that it
Take the corresponding number for a proton.
there's no new physics. It's lots of physicists think
that. It goes on for a number of decimal places because the experiment that can measure it so well. Now we have a theory of the protons recently developed involving forces and so on. We can't make any calculations.
I've got too many
yet. We haven't
tabs.
developed the technique good enough. So the best I could say, really, and probably exaggerating, is that the theory does say that this number should be around 3.
Fuck.
The error, and that's what I think it must be bigger. I can't prove that it's as small as it might be 0.3. That gives an idea of how sloppy our understanding of protons is compared to that that we understand electrons. All right? So that gives us some idea.
It doesn't seem to work like I expected. It should be full screen. But never mind. Let's try it. Oh well. I don't know why I'm doing this, but I wonder if I suppose Feynman's saying, I mean, all of this is described using the time-dependent Schrödinger wave equation. So it is all completely within the realm of quantum electrodynamics. There is no new physics, but the conditions wait and see. The conditions which it produces are some of the things that they've managed to observe just sound highly implausible. Like they're too fundamental.
Then I think it's time to start. Nobel laureates in physics and chemistry, laureates in economic sciences, your excellencies, members of the Academy, ladies and gentlemen. On behalf of the Royal Swedish Academy of Sciences, I wish you all welcome to the 2023 Nobel Lectures in Physics and Chemistry and the lecture of the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel. Alfred Nobel was an inventor, an entrepreneur, a scientist and a businessman, as well as an author writing poetry and drama. And in 1895, he devoted his fortune to 5 international prizes, reflecting his own international experiences and activities. And the first Nobel Prize was awarded in 1901, that is over 120 years ago. And the Nobel Prize in Physics is awarded for discoveries and inventions, and in chemistry for discoveries and improvements that have conferred the greatest benefit to humankind. And the Sveriges Riksbank Prize in Economic Sciences, or in memory of Alfred Nobel, was instituted in 1968. And we are pleased to see you all here to listen to the Nobel Prize and Economy Prize lectures. The past year, 2023, has been a dramatic year, with many crises ongoing at the same time. We have a climate crisis with the warming of the climate, an energy crisis, and we are fighting against inflation that poses a burden to the economy. We have a war ongoing since 2022 in our neighborhood in Europe, and the war that started recently in the Middle East, both leading to humanitarian was only possible due to scientific discoveries and many years of work on this new knowledge we could get. But the current turbulent world underlines the importance of enabling new discoveries, inventions, and improvements that benefit humankind, and also stresses that research must be local. Scientific discoveries are driven by curiosity and need insights to generate new knowledge. And it's impossible to determine what we discover in the future. Moreover, we don't know what the next challenges to humankind will be. Therefore, we need to prepare and the road to discovery can be long and wide, but can lead to unanticipated surprises and openings that were
Got
not
turquoise
considered.
beads on her necklace.
And we have seen groundbreaking discoveries during the years, and we now have the privilege and honor to listen to exemplary researchers and laureates who have increased our knowledge fundamentally and broadened our views in 3 different areas of research. The laureates of this year's Nobel Prize in Physics explore the world of electrons, inside atoms and molecules, and they managed to produce light pulses that are so short that they are measured in attoseconds. And these short pulses of light can be used to measure the rapid processes in which electrons move and change energy, previously not possible to follow. And attosecond pulses can also be used to identify different molecules, for example, in medical diagnostics. In the Nobel Prize in Chemistry, the laureates have discovered and developed quantum dots. And these nanoparticles are so small that their properties are determined by quantum phenomena. And they have many fascinating and unusual properties, such as having different colors depending on their size. And quantum dots are now being used in many applications, such as television, in lab labs, and also to guide surgeons when they are performing surgeries, such as removing tumors. And the laureate in this year's Prize in Economic Sciences has uncovered key drivers of gender differences in the labor market. And the laureate provided the first comprehensive account of women's earnings and labor market participation, and demonstrated how and unraveled why gender differences in earnings and employment rates have changed over time, and main sources for the remaining gender gap. All these achievements not only bring new knowledge and deeper understanding, but also allow us to improve our societies in multiple ways and to take wiser decisions. And we will now listen to these prize lectures by these exceptional researchers on whose shoulders present and future humans can stand, and whose giants in research will surely arise. So once again, most welcome, and my warmest congratulations to the laureates. And I now invite my colleague in the Academy of Sciences, Professor Eva Olsson, who is the chair of the Nobel Committee for Physics, to introduce the laureates in physics.
Honored Nobel laureates, Your Excellencies, distinguished colleagues, ladies and gentlemen, a warm welcome to the Nobel Lectures in Physics. And the prize in Nobel Prize in Physics this year is about attosecond physics. And attosecond physics is about
Oh yeah, hi.
very
Yes,
small time scales. So small that
15 zeros and then a 1 after the decimal point.
is the same number as a second since our universe was born. Even though the time scale is so small, what is taking place on that small time scale is affecting our daily life because it determines properties in many different aspects. Attosecond physics reveals the life of electrons and their dynamics. And through the knowledge of what is happening on that small time scale and with the electrons, we get the ability and the knowledge to make new tailored materials. We also can design electronics using new concepts, and we can develop methods for medicine of most importance for mankind. And our laureates, they discovered that it was possible to generate these very short light pulses. They developed methods to measure
It's the Nobel Prize lecture for physics from Stockholm. It's a live stream.
Isolated light pulses of the attosecond duration. And our laureates in physics, we see here, and I get some help to switch to the next.
That's the URL. I guess I should have put it in the description so that
And while we're figuring out how to go there, so
you can click on it, but I didn't think of that.
yes,
I didn't think anyone would show up.
Nobel laureates in physics this year is Pierre Agostini, Ferenc Krauss, and Anne Levier. And it is my pleasure now to introduce our first speaker, and this is Anne Levier. So please join me in welcoming Anne. Well, good morning. It's a pleasure to be here, and let me start by thanking the Royal Swedish Academy of Sciences and the Nobel Foundation for this prize.
How's that possible? I can never post links on other people's streams. Have I just enabled
So I will
link posting?
we arrive to this
I must have.
process. This is
Thanks anyway.
theory of attosecond science with the first years progress in technology and in understanding measurement of attosecond pulses and then opening to research fields and applications. And I will go through the first two parts and leave part 3 to my co-laureates, measurement of attosecond pulses. I will in the end just say a few words about some applications. Nothing would have happened without the invention of the laser in 1960 by Theodor Meinmann, and the Nobel Prize in Physics was given to the background for laser in 1964 to Towns, Bazov and Prokhorov. And you have here a picture of one of the first lasers, a ruby laser. Now what we are going to use in our research, the properties of the laser are first the possibility to generate short laser pulses, and especially the possibility to, by focusing these pulses, to achieve a very high intensity. So the invention of the laser led to new research fields, and the first one is nonlinear optics. This is a picture of an experiment.
I don't have much of an idea what it's about either. This is really seriously next level complicated shit.
And you see a ruby laser, which is focused by a lens into a material, and our experiment will look very much the same. And then the radiation is analyzed by a prism and detected by a detector. In this process, an atom absorbs 2 photons, it's a nonlinear optical process, and emit
a photon at frequency 2 omega. This is second harmonic generation, the first nonlinear optical processes that was discovered. Now, another research field that started after the invention of the laser is atoms in strong fields or multiphoton processes that were predicted already in 1934 by Maria Goeppert-Mayer. And in the multiphoton processes, an atom absorbs several photons simultaneously. It can be excited, it can be ionized. In 1979, Pierre Agostini discovered the process of above threshold ionization, where an atom is ionized by absorbing more photon that is necessary for ionization. And this is detected by observing electrons, and one observes several peaks. Now, an atom can also be multiply ionized, and this was actually my thesis work at the beginning of the 80s. Now, at that time, the question arose, is it possible to produce excited atoms or excited ions that then would decay by emitting fluorescence light? So we set up an experiment. This was in France, at the Commissariat à l'énergie atomique. We set up an experiment to observe this fluorescence light. Fluorescence light is emitted in all directions, so we had actually two axes of detection, one along the direction of the propagation axis of the laser with a grating and a detector, and one perpendicular to it. And this is the laser that was used at that time, an EDM YAG laser, 1 micrometer wavelength, and pulse duration was 40 picosecond. You have an oscillator here and 2 amplifiers. And this is a picture of the experimental setup. You have a laser is coming from the right. You have a lens focusing the laser into a chamber, and the radiation is detected along the propagation axis with a grating and a detector and perpendicular to it. The intensity reach in the medium, so here we have also a pulsed gas jet delivering some gas of atoms. So the intensity in the medium reached several times 10 to the 13 watts per square centimeter, which is quite high. What did we see? Well, we never saw anything perpendicular to the detection axis, so I'm not going to discuss that anymore. And we didn't see much fluorescence. What we saw was very high order harmonics of the laser field. And this is one of the first spectra obtained in argon gas. And what you see here are harmonics 13, 15, up to 31st harmonic of the laser field. So when it says 13 here, that means that the frequency is equal to 13 times the laser frequency. Now, if we plot the intensity distribution of these high harmonics, we get typical behavior with the decreased plateau behavior where all the harmonics have the same intensity, and this is ending with a cutoff. And this was very unexpected. First, it was not expected to see so many high order harmonics. Then, it was not expected to have this plateau behavior. One thought that it would be more and more difficult to generate high order harmonics. This was based on some kind of perturbation theory thinking at the time, that based on an expansion of the polarization induced in the medium in powers of the electric field, for this expansion to be valid, has to assume that the first order is much larger than the third and much larger than the fifth. And this was not the case. You can notice that I'm only talking about odd orders of the laser, And this is due to a symmetry property of the medium. It has the inversion symmetry, so the even order harmonics are actually killed. Now, if you go from
actually what?
Frequency of the laser light, which is in the infrared region, and you multiply this frequency by, let's say, 33, you end up in the extreme ultraviolet region of the spectrum. So it's below X-rays, but above ultraviolet light. So this light is invisible, and it does not propagate in air, so we have to evacuate. Now, let's make a little bit analogy with music
look at the
here.
lights on the desk.
When we think about harmonics, usually think about music. What we do is actually very similar to what happens when the bow of a violin hits a string of the violin. It produces not only a single tone, but also overtones. And this is what actually makes the clang, the timbre of a music instrument, is how many of these overtones we have. In our experiment, we produce not harmonics of sound, but harmonics of light. And the violin is the gas of atoms, and the bow of the violin is the laser pulse. Now, this process requires to it at the border of two fields, atomic physics and nonlinear optics. Atomic physics is the description of the response of an atom to the laser field, and this is, we are in the quantum world. This is described by a Schrödinger equation that you have here, where you have here the atomic potential and the laser atom interaction. In this problem, we can describe the laser field classically, and we use the dipole approximation. Now, the second aspect is in optics, the response of many atoms to the radiation. It's not enough that each atoms generate these high harmonics. You also need to have efficient harmonic generation to have the emission from all of the atoms in the medium in phase, act coherently. And this is described by Maxwell equations of electromagnetism, which can simplify to a wave equation as what is written here. E here is the generated field in the medium, and P is the polarization in the medium induced by the laser field. So the first attempt, let me say one more thing, again, analogy to music. This many atom response, you can think of a gigantic orchestra. All of the musicians in this orchestra need to play with the same pace. And the number of atoms in this orchestra is trillions of atoms, many more than the number of people on Earth, just to give you a little bit an order of magnitude. Now, the first attempt to describe these processes was to simply solve these two equations which I just wrote. And these are calculations of this single atom response, solving numerically the Schrödinger equation. And you see that the agreement between theory and experiment is quite good. In itself, it's a bit surprising because at that time we thought that the many atom response would be very different for the different harmonic order. It would be more and more difficult to phase match the process. So it was really necessary to also solve the second equation, the wave equation. And this is what was done here. You see that we obtained a rather good agreement again with the experimental behavior, and we can reproduce this plateau and cutoff behavior. So we can simulate the experiment, but we don't really understand the physics behind. Approximately at the same time was asked the question, could it be that these high-order harmonics form in the time domain a series, a train of attosecond pulses? And the idea is the following. Consider, let's say, 3 harmonics, 17, 19, and 21, and assume harmonics are all in
Pythagoras,
phase
isn't
at a
it?
certain
The
time.
music.
They are phase locked. If they are in phase, synchronized at a certain time, they will be again in phase after half the laser cycle. So now if you sum these three waves, you see that we get constructive interference when they are in phase and destructive interference where they are not in phase. We can confine the light into short pulses. And if we plot the intensity corresponding to this electric field, you get a
That would
train
sound
of
good on a
attosecond pulses.
synthesizer.
If you sum not only 3 harmonics, but let's say 10 harmonics, and you assume they are phase locked, you obtain a train of very short light pulse. Why is it interesting? Because the evolution of the pulse duration of lasers had come to a stop. This is the evolution of the pulse duration of dye lasers decreasing from picoseconds down to a few femtoseconds, and a couple of years later, titanium sapphire laser would also arrive at the stop of about 2 femtoseconds. And the reason for this stop is that we are talking about light pulses. And to talk about a light pulse, you need to have at least one optical period in this pulse. And the optical period of, for example, a titanium sapphire laser is 2.6 femtoseconds. So in order to decrease the pulse duration, you need to decrease the optical period, which means to go to higher frequencies. Now, the second condition to get short pulses is that you need a broad bandwidth. This is just an expression of Heisenberg principle. To get a short time, you need a broad bandwidth. And these high order harmonics provided both higher frequencies in the extreme ultraviolet and the broad bandwidth, this plateau behavior. So this was a very exciting question. So now I'm coming to the second part of this talk, which is progress in understanding and progress in technology. And I would like to start by progress in technology. At the beginning of the 90s, there was a huge progress in laser technology. First with the chirp pulse amplification, which led to a Nobel Prize to Gérard Moreau and Donna Strickland in 2018. There was the discovery of a new material, titanium sapphire, by Peter Moulton, and then a new way to generate short pulses in the laser oscillator, which was Kerr-Lenz mode locking. And here you have 3 Swedish scientists, Sune Svanberg, Anders Persson, Claes-Göran Wahlström, that look at this new laser technology, and they decide to really invest into this new laser technology. This was very risky because it was not clear that it would work, but they really invest into this technology and build the high power laser facility in Lund with terawatt titanium sapphire laser. This was really the perfect laser to study high order harmonic generation with a short duration of the order of 100 femtoseconds, and at that time a high repetition rate, 10 laser shots per second, 10 hertz. In parallel to that, there was also a progress in instrumentation. In Saclay, we built a dedicated instrument to study high order harmonic generation, which you see here, and these instruments include gas jet, optics to analyze the radiation, and a detector. And here you have myself, much younger, together with Philippe Alcou and Pascal Salière, my first PhD students who are here in the audience today. And this is also the time where personal computers came into the laboratory. The first experiment that I mentioned, we were using a printer to record the signal. Now, personal computers started to really come into the lab, and we could, thanks to these computers, really take data in a very completely different way. So we performed, so this led to very nice experiments combining this dedicated instrumentation and this new laser system, titanium sapphire. And I show here one of the first spectrum obtained in neon using this laser by a group in Stanford. And you see a beautiful harmonic spectrum with a very large plateau here. This decrease at the beginning is simply due to the decrease in efficiency of the grating, and you have the cutoff in this region. So you see that we go to the 111th harmonic. And in Lund, together with the collaboration Lund and Saclay, we could not only take harmonic spectra, but really study these harmonics as a function of different parameters. For example, here as a function of the laser intensity. Now, approximately at the same time came really a breakthrough in the theoretical understanding of this process with the three-step model. So I would like to say here that this prize is given to the experimental method in attosecond science, but the theorists have played a very, very big role in attosecond science, and in particular in the understanding and this three-step model. And this was shown probably at the same time by Ken Kullander and Ken Schiffer, by Paul Horkum in Canada, and Maciek Levenstein and co-workers here, Misha Ivanov, presented a quantum formulation of this three-step model called the strong field approximation, which was going to have a very strong impact in the field. So this three-step model is presented here. What happens is that you have an atom in a strong laser field, and this laser field is really strong. It distorts the atomic potential. It's bend this potential, and here you have a barrier. So an electron in the ground state, this is quantum mechanics, there is a certain probability for the electrons to tunnel through this barrier. Then the electrons is driven away by the laser field. The laser field changes sign, the electron is pushed back towards the atom, and then there is a certain probability of recombination. In this excursion, the electron has gained some kinetic energy, and the excess energy is emitted in the form of a high energy photon. And this process is repeated every half laser cycle on one side and the other side, and again, leading to emission of light every half cycle of the laser. Now, what about attosecond pulses? I just remind you that we have discussed that if we had phase-locked harmonics in the time domain, we would have one pulse per half cycle. So what was this new theoretical understanding telling us? And here is the bad surprise. This was the result of the calculation. Light everywhere, no one pulse per cycle, so no phase-locked harmonics. So the attosecond idea at that time was quite controversial and not so clear. How can we understand this multiple pulse emission? Actually, we can understand very simply using this three-step model and looking at the possible electron trajectory. This is just a very simple picture of these trajectories, electron going out and coming back. I put in colors the energy that the electron have when they return. So you have higher and higher energy depending on when the electron is born. But there are also trajectories which takes longer time and leads to a similar type of energy. So when you look at the possible trajectory, you find that there are short trajectory and long trajectory leading to the same kinetic energy. And this complex picture leads to this complex result in the time domain. Now we could actually verify the existence of these trajectories in the laboratory. This is an experiment performed in Lund in 1998, and you have some of the participants here, Mette Gårder, who's in the audience, Ted Hensch, Marco Bellini, and others. And what we did in this experiment was to look at the coherence of this high harmonic. Is it coherent light? And to do that, we duplicate the harmonic sources, and we look at whether this light interfere in the far field. If this is coherent, we should have interferences. And indeed, you see here on the 15th harmonic that there are beautiful interference fringes. What you can also see in this picture is that there are now two contributions. There is collimated radiation and more divergent contribution, which we could identify to the contribution from the short trajectory and from the long trajectory. Now we could also delay one of the source relative to the other and look at what happens to the interference fringes. And you see that in this case, the interference are still present for the collimated radiation while they are gone for the more divergent contribution, which shows different properties of these two contributions, short and long trajectory. What happens to the other side?
I'm lost.
Strong field nonlinear optics, the response of many atoms, was also a progress in this part as well. So to achieve fast matching here, we need the phase of the pulse which is generated to be equal to the phase of the polarization induced in the medium. So we need these two wave vectors here to be equal. And this difference in wave vector depends on the dispersion in the partially ionized medium, depends on the laser focusing, but it also depends, and that's the important thing, on the electron trajectory, whether it's short or long. And this gave us the idea, or maybe in some condition, only one of these trajectory can survive, only one of these trajectory get phase match. And indeed, this is what we got. This is, in dashed line you have the single atom response, while in blue you have the temporal structure of the total attosecond pulse stream. So we recover 1 attosecond pulse per laser half cycle and phase-locked harmonics. So at this point, we think that, or maybe we have attosecond pulses, but what is very important is to measure attosecond pulses. Before I come to the conclusion of this talk, let me point out that at the end of the 90s, there is a lot of progress, both in laser and in high-order harmonic technology. And let me just flash some of this progress. First, now we can generate laser pulses that are very short, few cycles, and then the importance of the carrier envelope phase is pointed out. The carrier envelope phase is the phase offset between the electric field and the envelope, and this was going to be very important for the generation of single attosecond pulses. Then you have novel medium geometries like cell or capillaries. You have also new media that are being explored, molecules. You have a push toward higher photon energy using short laser pulse and especially long wavelength lasers. And you have also a push toward higher pulse energy in the microjoule range using clever focusing geometries. So now I am going to jump over this part 3, and I would like to finish this presentation by just giving you 2 examples of application. Very different example. One is very fundamental. This is about electron dynamics, and one is much more applied. So dynamics. I think that's the exciting thing about attosecond pulse is we can now follow the dynamics of electrons in matter. And here I take one example, which is very simple. It's photoionization, a process that was understood theoretically by Albert Einstein in 1905, and he actually got the Nobel Prize just for the discovery of the law of the photoelectric effect. So what we can do, and I'm going to talk about photoionization of atoms. What we can do, thanks to attosecond pulse, is we can now answer a question: how long time it takes for an electron to propagate in the continuum? What are the wave quantum properties of the photoelectron? And I'm not going to explain how we do these measurements. I just want to try to make you understand what we can do, again by using an analogy with music. In music, you keep the pace by the conductor is keeping the pace, or a metronome can be used to keep the pace, and the metronome has a motion like this. So this is a wave motion, both the conductor and the metronome, which is due to the mechanical motion of the tip of the metronome. And this is exactly what we do. We are looking at oscillations, such as this one here, and we are going to compare the position of the maxima of this oscillation and this oscillation. Here I'm talking about photoionization of neon atoms in the 2s shell, which I'm comparing to photoionization of neon in the 2p shell. And what do we measure? It's always interesting to talk about time by showing a clock. In our measurements, 1 hour on a clock is 1/2 period of the laser, which is 1.3 femtosecond. So 1 hour is here 1,300 attosecond. And what we can measure very accurately is the position of two arrows on this clock, which correspond to the time it takes for the electron to ionize from the 2s shell and from the 2p shell. We don't know where these two clocks are on this clock, but we can measure the difference in time between these arrows. And now I'm showing some results showing that indeed we can measure this relative time quite accurately within tenths of attosecond. The second application I would like to mention is really going into a completely different direction now, very applied, and this is now belonging not to the research laboratories anymore, but to industry. And this is an application not so much about the temporal structure of these high-order harmonics, not so much about attosecond path, but about simply an application of this radiation, which is in the extreme ultraviolet range and which is very broad in frequency. So now harmonic generation are being used to control wafers, silicon wafers, which contain integrated circuits, and this technique is used for the next generation instruments that will control this integrated circuit with very, very small dimensions of the order of 10 nanometer or below. And this control is made not only in 2D, but in 3D. And what is really used here is the fact that we have so many frequencies. And this is developed by an industry, ASML in Holland. Now, to conclude, I would like to thank many people, all of my colleagues during all of these years. And I'm showing here some group pictures, not since 1987, just the last 15 years or so. I would like to also thank the organizations that have funded this research, the Swedish Science Council, Swedish Research Council, and the European Research Council, the Wallenberg Foundation. And last but not least, I would like to thank my family, Claes-Göran, Oscar, and Victor. Thank you for your attention.
Wow, that was good. I hope they leave it on so they can watch it again.